2, 1. Okay, here we are. As promised, pre-recorded video, and it should be the last one, so that's exciting. Alright, so what are we going to talk about today? We're going to keep talking normed vector spaces, which we introduced in class earlier this week, and our goal is to talk about norms for matrices. We kind of set that up as initially what we were after, but obviously we want to study things with a bit more generality. So let's recall the definition of a normed vector space. So a vector space equipped with a function, which we call a norm, where this is basically mimicking the properties of length that we saw in Euclidean space. So specifically, the norm of a vector is always non-negative. The only time it hits zero is if we have the zero vector. Scaling a vector appropriately scales the norm. So right, again, we want to think of this as length. So if you scale something, well, then the length is either going to be stretched or compressed by the same factor of alpha, but flipping it with a negative real number there is not going to affect the length. So that's why the absolute value is showing up. And then here we see the good old triangle inequality. In effect, the length of a sum does not exceed the sums of the individual lengths. And again, just draw the triangle. We know this to be true. All right, so other things we know to be true. Rn is a normed vector space, and there's a lot more than just the usual Euclidean distance that's built off of the dot product being an inner product and thus giving us a length, and also just geometrically it's the Pythagorean theorem in disguise. There are other lengths that you can slap on your normed vector space, and as we discussed, there is a whole profusion of them for every real number between 1, including infinity. Then we can form norms as follows. So for when p is not the infinity symbol here, then it's the p norm, where you take the pth root of the sum of the pth powers. And then in the case of infinity, well, then you just take the maximum of the absolute values. Right. And we established all of these, in fact, have to be norms. Now, we didn't prove the triangle inequality. We stated it and noted that it's called Minkowski's inequality. And we proved all the inequalities that let you get there. In the interest of moving on, the type notes have the full-on proof of the triangle inequality for all the p-norms. Note that in class we did the one norm because it's super easy. The infinity norm also is in the type notes for those of you who are interested. But these are norms. It takes a little bit of effort to prove that they're norms outside of the case of 1, 2, and infinity, but it's not too bad. Alright, but now this raises an interesting question. These are all obviously very different functions, right? Although there is sort of a similar pattern. Taking the square root is incredibly different from taking the cube root, right? Square root cannot handle negative numbers if you want to keep things real, while cube root can, right? And obviously there are p-values that are not rational numbers. So for example, pi is hanging out in here, so I can talk about the pi root of something, but that is an incredibly different beast than square rooting or cube rooting. Or even taking, like, the 5/3 power of something. So, they're clearly incredibly different, and even in the infinity case, this is just a completely different formula. So we want to understand how different they really are. And what's incredibly shocking is that the answer is they're actually not. And in fact, we're going to prove that in all senses, they are essentially the same thing. Even though the computation is different, their sort of qualitative behavior is going to be the same. That's pretty interesting and exciting. Now, in order to get there, let's prove some things. Alright, so first off, let's begin with a couple of proofs of general normed vector spaces. So, last time we gave the definition, and we focused our attention on creating examples. Let's now start getting some general properties. So one property is that the length of a difference is equal to the length of the same difference, but in the opposite order. Right, so x minus y is generally not equal to y minus x, but here we see the norms line up. And intuitively, if we're thinking about norm as representing a length, this quantity right here is representing the distance between x and y. And so the fact that these line up is saying it doesn't matter how you measure distance from x to y or y to x. And then the all-time classic reverse triangle inequality, saying that for differences, we have a inequality, but it goes in the other direction, rather than the norm of a length here being less than something. Here we see the length being greater than the absolute value of the difference of these two. Alright, and this is a useful result that we're going to repeatedly use. So let's get to the proof. So first of all, this one's super easy because we recognize that the difference of two elements is the same thing as scaling by -1. -1 can be pulled out, and the absolute value of -1, of course, is 1. Ta-da. Not the most exciting proof, but we got it. The first triangle inequality, on the other hand, has got a pretty fun proof, one of my favorites. Because it begins with the all-time classic math trick. I'm going to add 0, and I'm just going to be very smart about how I add 0. So we start with x. We recognize that x is x minus y plus y. That's less than or equal to this quantity, and thus I can subtract that over. And likewise, appealing to point 1 lets me swap x with y, and essentially end up with the same thing on the right-hand side, both the x's and the y's swapped. So, if I subtract y over, I get this inequality. And if I subtract this over and subtract y over, I instead get this inequality. And here we see that this number is bounded above and below by a number, and it's negative, so that means its absolute value must be encapsulated by that number. Pretty cool. Really neat proof. Always love the proof of the reverse triangle equality. So it's a neat low one. And the consequences of this are quite nice, as we're going to see. Okay. Alright, so as we mentioned, quantitatively, the p-norms are incredibly different from each other, but I'm claiming that qualitatively they are essentially the same thing. So how are we going to measure that qualitativeness? Alright, well, we're going to measure it using my favorite idea in mathematics, convergence. Ooh. Well, it shouldn't have been no shock that limiting processes would be the qualitative thing we're going after, even though they are somewhat quantitative. There is a bit of a qualitative aspect to them. So it's going to turn out that the p-norms are equivalent to each other in the sense that convergence does not care about which measure of length you use. So as we noted, if you have a notion of length, you have a notion of distance between elements. Here we see that going on. So, with a notion of distance, we can have a notion of convergence. So, given a sequence in an R vector space, we say that it converges to an element if, given an epsilon, there is some point where the distance between them gets arbitrarily small and stays arbitrarily small. So, given an epsilon, there is a capital N, so that blah 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 happens, right? But again, the big picture here is, how close do you want to get? I can guarantee that I always get that close, and I stay that close. So this is the guarantee that I get that close, and then this is the guarantee that I stay that close, and here's the measurement of how close we want to be. Alright. So, let us now prove a very important proposition. One that I think is, I don't want to say inarguably, one of the most important proofs you're going to see, but a theorem that I feel serves a very important purpose and covers a lot of different math ideas. So I was at a conference once, and this guy from UNI, TJ Hitchman, he was giving a talk, and I think he posed the broad question to the crowd of what's the most important proof? Right, and that's a very loaded question, because depending on what you mean by most important, it's going to be, like the most significant mathematical achievement human beings have been able to create, which one to you personally matters the most, or which one is sort of a kind of like, well, this covers enough broad strokes of like, well, this should be considered the most important proof. This one, I feel like, lands on a lot of things. Because, first of all, let's dissect the statement. Given a sequence that converges to two things, the two things have to be equal. Right, and that's something that we sort of immediately take for granted when we're talking about convergence, right? When in calculus, we're like, oh, the limit. Right, but how do you know it's the limit? How do you know there's not other possibilities for the limit? Right, sort of intuitively in the definition, it feels like there should only be one thing, but note the way we said it. You converge to x if this happens. I didn't say that, right, we are convergent to exactly one thing. There is only one thing. The definition is there is a thing that works. Doesn't say it's the only one. Right, so this is sort of a necessary proof that is needed. We need to verify that, yeah, if you converge to something, that's it. You can't converge to anything else. And shockingly, you can set up a notion of convergence where you actually converge to multiple things. Right, a world you don't want to live in, but a world that exists. And so first of all, right, so why I feel like this is the most important proof, there's that part of it, the sort of like pedanticness, but pedanticness with a purpose. The techniques we're going to see in this proof are universal to any sort of convergence arguments. So we begin with my favorite opening sentence, let epsilon be greater than 0. What do we know? Well, let's unravel the definitions. Well, if we're converging to x, that means I can get my sequence as close to x, and it can stay as close as I want, so there is an end, so I can get close. And here we see our first interesting little thing. Epsilon over 2 is a positive number, so, right, it doesn't just have to be epsilon. I can put whatever positive number I want here. Similarly, we converge to y, so there is an m that works, and again, we just need a positive quantity. It doesn't specifically need to be epsilon. Then we notice that, hey, I have 2 points where my sequence is getting arbitrarily close. I can always find the maximum of those 2 things. And that point that is the maximum obviously is both bigger than n and m. So these distances get less than epsilon over 2. Less than epsilon over 2. And note that hey, those add up to epsilon. Hey, I have 2 pieces and I divide by 2 and I add them up. And so here we see, using that definition, using the fact that we get far out enough in the sequence and then we guarantee that we get close enough. And what I'm doing here is showing that the distance from x to y can be made arbitrarily small. And right, this reveals another important technique. I'm proving that 2 things are equal, not directly, but rather indirectly. I'm showing they're equal by an inequality. Because epsilon can be as small as I want, so this has to equal 0. It can't be any smaller. Or it can't be anything other than 0. That's what I meant to say. And if that equals 0, then, well, it's a norm. So we know that you have to have the additive identity, and thus x is equal to y. So, in terms of most important, this proof, to me, definitely lands in that category, right? It's not overly technical. It doesn't involve some wacky trick that you wouldn't, in a million years, ever think to do. Right, it's a simple, well, start out with, what do we know about convergence? You need epsilon, so start with epsilon. From that, you can get your ends, right? Just unraveling the definitions. And then there's kind of the subtle note of like, oh, well, I could take the max of these 2, and so then I can get far out enough in the sequence where I'm close to both things. The epsilon over 2, right, this is now a common theme that will happen a lot in convergence proofs where you have multiple pieces and each piece is getting small. So depending on how many pieces you have, you need to account for it to get a nice clean epsilon in the end. And then this sort of, again, very powerful idea of getting equality using inequality. It's a very powerful tool. So there's a lot of amazing techniques here that are widely applicable to not just the material we're talking about, but other courses that you're going to be in. It's a very, very important proof to me. I feel like there's a lot of important themes and skills on display here. So it's a good one to really stare at and study. And obviously I've left it here and rambled incoherently so you can look at it. Or swivel around in your chair and not pay attention and wait for the next thing. Whichever you're doing. Or if you've got this video on 1.25 speed, I don't blame you. Alright, cool. Well, like I said, one of the features of this, one of the reasons I like this, it's pedantic with a point, because now we know that if you have a sequence and it converges to something, it can only converge to one thing, and that allows us to introduce the idea of the word limit. Right, so a sequence can only converge to at most one thing. Either it does converge to something, or it doesn't. And the thing it does converge to, well, we'll say the sequence is convergent, and it converges to its limit, which we denote as the limit. And as needed, we'll just abbreviate this to lim of x sub n, where you understand that n's going to infinity. We don't need to write it all the time. And this will allow for sort of cleaner inline equations. Alright, so there we go. We have a notion of limit now in a normed vector space. And as promised, what we're going to eventually show is that limits in Euclidean space don't care about which p-norm you pick. That's quite shocking. Alright, but before we do that, let's now get a litany of results regarding limits. So what are these statements here? Well, these are just saying that limits interact with the structures of a normed vector space accordingly. And by that I mean the limit of some scaled sequence is the scaled limit, the limit of a sum of two sequences is the sum of the limits, and limits can be brought into the norm. So the three relevant structures of a normed vector space, the scaling, the adding, and the norm itself, are all appropriately interacting with the limit operation. So that's quite nice. Oh, look, I could pull out scalars and break out sums. I wonder if limits are linear. That's exciting. Alright, now I have the proof of all three of these typed up in the typed notes. For the sake of not having a video that's 5 hours long, we're just going to prove one of these again just to get a little flavor of how these proofs work. I'm going to go with number 2. So let epsilon be greater than 0. Then we can find n and m so that the sequence x sub n gets close to its limit, and the sequence y sub n gets close to its limit. And then again, we pull the same maximum trick. We have two epsilons, we look at the difference, and we pull it apart accordingly, and life is good. Nothing too crazy, but again, here we see those techniques on display. These limiting multiple quantities, picking the maximum, and using the triangle inequality. Like, I can't even begin to tell you how many proofs are just literally this format. And being able to like master this and have a good idea of how all of this works is, you're gonna go far, kid. Side note before we move on, so this is a 2 epsilon proof, right? There's 2 epsilons. If you go to an old book, they actually don't bother with the dividing by 2. They get like 2 epsilon in the end, and then they're like, oh, and then, epsilon can be replaced with epsilon over 2. It's a more modern convention to kind of make it all clean up nicely in the end. Which might be a little, at first, jarring when you're first learning this stuff, because you're like, why the hell am I doing this? Other than, oh, in the end, it's nicer if you do this. That being said, one more fun story. I went to a talk once, and the talk was somebody doing a 10 epsilon proof. So they had 10 things, and each thing they proved was less than epsilon over 10. That was their entire talk. Each slide was this is less than epsilon over 10, this is less than epsilon over 10. It was amazing. I don't even remember what the hell they were proving, but I just remember being like, oh my god, they're doing a 10 epsilon proof. This is insane. That was pretty cool. Yeah. Unfortunately, we're not going to go beyond the 2 epsilon proof for us. That's unfortunate. But if you're enjoying this stuff, then when you take off Math 414, oh boy, you're gonna have a good time. Alright, so another thing about sequences that's important is this notion of subsequence. So given a sequence, a subsequence is formed by replacing the indices down in the denominator instead of 1, 2, 3, 4, 5 with just some strictly increasing listing of numbers. So a common one is like the even numbers, so you do like 2, 4, 6, 8, so on and so forth. And notationally, this is usually written as x sub n sub k, where it's understood that there's a function whose output is n sub k. But it is worth reminding ourselves that sequences, again, are functions themselves, and so this is kind of just a composition of 2 functions. And I don't know what's going on with this notation right here. That's wacky. I didn't even catch it. I converted over from the type notes to the slides, and I went through and I cleaned them up as I was going. I modified some things and changing stuff, and still, dude, freaking junk always gets through. And why isn't this changing? Oh god. And understood isn't spelled right. That's 10 out of 10. Understood. Alright, sweet. Okay, now, why would you even care about this? Well, it turns out there's actually some interesting things you can do with subsequences. And a quick and easy proof is that if you have a convergent subsequence, any subsequence converges to the same thing. And the proof of this is quite simple. Given an epsilon, there is an n so that we get close. Alright, well, take anything bigger than n. N sub k has to exceed n. If you're strictly increasing, you're always greater than whatever your input was. Right, think about like the even example, right? So 2 is the first output. Well, it's bigger than 1. 4 is the second output. Well, that's bigger than 2. So on and so forth. Right, and you can imagine a goofy subsequence where you, like, have 2 and then 4, but then you, like, immediately start just counting 5, 6, 7, 8. Like, you skipped a couple of numbers initially, but then you get back in line. Right. Or, you don't start strictly increasing until much later. Like, you start with 1, you start with 2, you start with 3, you start with 4, but then at 12 million, all of a sudden you jump to 14 billion or something like that. You're allowed to do that. It's totally legal. But anyway, yeah, so every convergent subsequence, every convergent sequence, all their subsequences converges to the same thing. However, the converse of that is not true. But we have actually quite an interesting statement about subsequences and convergence that we are going to exploit. Which is the following. So, for sequences of real numbers, we have the all-time absolute classic, probably one of the most important properties of real numbers. The consequences of this theorem are far-reaching, and you can't even begin to comprehend how absolutely essential this thing is right here. So this is known as the Bolzano-Weierstrass theorem, and it says that if you've got a sequence whose outputs are stuck between b and negative b, where b is some positive real number, then there's a convergent subsequence. Now, at first glance, this does seem to be kind of just a amalgamation of math words. But you're going to be shocked at how powerful this is, even for what we're talking today. So once you take Math 414, you're going to see this is the go-to. You get away with so much stuff with this theorem. But first, we'll see. It's an incredibly powerful result, and like I noted, as stated, it does seem to be just a bunch of words put together, but it is insanely powerful. Alright, now I don't want to get into all of the details of this, but I'll give you a quick outline of the proof. On the type notes, I've got the full-on proof. But basic idea is as follows. You look at your sequence, and then you look at your sequence's tails. And what that means is you look at the full sequence, which would be E1. Then you look at E2, which is the sequence starting at 2. So you ignore the first term. Then you look at E3, which is the sequence starting at 3. E4, sequence starting at 4, so on and so forth. Now, the idea here is that each one of these is contained in the interval negative b to b, so you can make the interval as small as possible and still containing e. So for the people that are interested, we got the infimum and the supremum hanging out right here. Ooh. And then what you can verify is that the sequence of right-hand things converges. The left-hand ones also have to converge to something. And then what you do is you inductively create your convergent subsequence. We can find an element that is greater than b1 minus 1 out of e1, because this is the smallest upper bound, so if you make it smaller, it's no longer an upper bound, so we can get something bigger. Then you go to the set en1 plus 1, because you need your n2 to be bigger than n1. It needs to be strictly increasing, right? And you can get this element to be within 1/2 of that, and then you just keep going with a third, and eventually you create a subsequence where this is less than 1 over k. The b sub n's are convergent, so this subsequence of them is also convergent to the same thing. But this is getting really close to that limit, so this must also get to that limit because it's getting arbitrarily close. So this. So a very hand-wavy proof here. A lot of details need to get filled in, but that's the basic idea. Right, like I said, that's going a little bit further than we want to go. We want to get back to norms here, so let's do that. So, for our norm vector space, equipped with 2 norms, we need to be careful about when we say that a sequence is convergent, because what norm is the convergence with respect to, right? There's no reason to immediately think that 2 norms are going to always have the same convergence type, right? Numerically, we can see norms are very different from each other. So we want a way to compare convergence of sequences, and one way of doing that is with this notion. We'll say that one norm is dominated by another if that norm is always less than or equal to some positive factor of the other. So here you can kind of see, like, oh, it's being dominated. This is always less than or equal to that. Now, at first glance, this might seem maybe like a weird relation, and actually part of your brain might go like, does that ever actually happen? The answer is yeah, and it's super easy to see with our p-norms. The one norm is in fact dominated by infinity. Pretty easy to see because, hey, each one of these has to be less than the infinity norm, and hey, we have a factor multiplying the infinity norm bigger than our sum there. Quite interesting. And in fact, you actually have all the ingredients to prove that any p-norm is dominated by another p-norm using good old Holder's inequality. But let's talk about why norm domination matters if we have two norms and one's dominated by the other. If you are converging with the dominator norm, then you are converging in the dominatee norm. Alright. So you got a norm dom or something going on here. Alright, so and it's a pretty easy proof to see, because given an epsilon, we're going to show that this sequence converges to x with respect to the dominated norm. Well, the dominated norm has a factor of c, bounding it with the dominating norm. We're converging with respect to the dominating norm, so we know that that should be a b, not an n. What the... As always, man, there's always... Well, at least that's like the key right next to it on the keyboard. If it was a different one, that would be like embarrassing. Anyway, so we're converging with respect to the b norm, so we can get as small as we want. We need to account for the factor of c, so we're going to take our epsilon divided by c. I prefer to use etas for this. It's a very common thing there. And then if we look at the difference between x sub n and x in respect to a, we know that's dominated with a factor of c. This is less than eta. Eta times c is equal to epsilon, and thus we get our convergence. So here we see that if we have a norm A that's dominated by a norm B, then convergence in B will ensure convergence to the same thing in A. So as we just saw, if you're converging in the infinity norm, you're going to converge to the one norm, and you'll converge to the same thing. Quite nice. So obviously then, we want to introduce the following definition. Two norms are equivalent if they dominate each other. And at first glance, it may seem, well, how is that possible? As we will prove, this is the case for everything in Euclidean space. But for the one norm and the infinity norm, it's easy to see that, because we know the one norm is less than n times the infinity norm. And the infinity norm is always less than the one norm. The infinity norm is one of the elements, it's the maximum one. The one norm is the sum of all of them, so obviously it's always bigger. Alright, so here are some properties of equivalence that we're not going to prove in the video. It is in the type notes, but here we see that if norms are equivalent, then convergence with respect to norms doesn't really matter, because if the norms are equivalent and you converge, it doesn't matter which norm you're doing the convergence with, you're always going to converge to the same thing. Right. And here we see a more efficient way of determining equivalence, as that was traditionally written. And here we see an interesting thing. If we want to prove two norms are equivalent, one way of getting it is to show that there is a third norm that's equivalent to the two separately. So here we see that norm equivalence is transitive. In fact, it is an equivalence relation on your vector space. An equivalence relation on the norms of the vector space. Alright. So now we have a notion of equivalence of norms. Obviously, we want to set our sights on the p-norms and prove that they're all equivalent to each other. And in fact, what we're going to prove is that all norms are equivalent. I don't care what norm you create, it's going to be equivalent. So, in other words, in Rn, we can just say if you have a sequence and it converges, there's one thing it has to converge to, and it doesn't matter which norm you use to measure it. Now, obviously, this is incredibly powerful because it says that if we want convergence to happen, let's say in the Euclidean norm, I don't actually need to worry about it. I can just go to the infinity norm or work with that, which is obviously more computationally friendly because it doesn't involve square roots and squaring. And likewise, right, you can make that even more powerful. Let's say if you really were interested in the 5 norm for some reason, right, instead of actually dealing with the 5 norm, you can deal with the 1 norm, which is also easier to work with. So this is really a incredibly powerful fact and a very useful fact that basically convergence in Euclidean space can be measured however the hell you want. So convergence is sort of a universal property. There's no dependence on how you measure to get convergence. Very nice. Alright, so step one, we're going to prove that any norm is dominated by the infinity norm. Which, okay, I mean, yeah, that's kind of a nice symbol there for that. So we'll set C equal to the sum of the standard basis elements norms, and note that this has to be positive. The standard basis elements are non-zero, so whatever norm you have, those lengths need to be non-zero, so I have a sum of non-zero things. Strictly positive things. Alright, now take an element out of Euclidean space. Well, we know that we can write it as a linear combo of the standard basis elements. By the triangle inequality, we get this. Each one of these terms is less than the infinity norm. We can factor it out, and hey, there's our C value we were looking for. Alright, so the trick now that we're going to pull is prove that the infinity norm is dominated by any norm. And this is where we're going to have to pull out kind of some trickery to get this. So showing that any norm is dominated by the infinity norm is pretty easy to do, but the reverse requires a couple of maneuvers, and probably, I don't know, the Bolzano-Weierstrass theorem. So let's see that in action. So first things first, we're going to, we're not going to prove this, but we'll outline it. There are two sets that are always usually important when you're studying a norm. The set of things whose norm is equal to 1, and the set of things whose norm is less than or equal to 1. This is usually referred to as the unit ball of the norm, and this is usually referred to as the unit sphere of the norm. Right, and if you think of Euclidean space, that makes quite a bit of sense. Everything with length less than or equal to 1, well, that's the unit circle. For example, in R2. And in R3, if you're looking at all things that have length 1, well, that gives you the sphere centered at the origin. So, hence the S and the B. Alright, so these sets have a Bolzano-Weierstrass property, meaning that any sequence that is contained in these has a convergent subsequence. And that limit lives in the sets. A very powerful fact. Alright. Now, the proof of this is essentially just keep using the Bolzano-Weierstrass theorem. Because if you were to take your sequence, this is a sequence of elements in Rn, well, each one of these has components, so you just look at your components, and because we're bounded by the infinity norm, and the infinity norm is either 1 or less than 1, each one of these sequences of real numbers is bounded, so it's going to have a convergent subsequence. So in the first coordinate, you have a convergent subsequence, then you go to the second coordinate and find another subsequence and it's convergent, and then you repeat until you have a convergent sequence in each coordinate. And again, the typed out details of the proof are available, so check those out, but that's the basic outline of the proof. Now, why do I need this? Well, I need this to get my domination. So we know that the infinity norm dominates any norm. I'm trying to show now that any norm is dominated by the infinity norm. And that will get that the infinity norm and our norm are in fact equivalent to each other. Alright, so the trickery is going to be to, again, set up the sphere for the infinity norm. We're going to prove that our norm, when it's restricted to the sphere, has a minimum that is greater than 0. So in other words, the norm of any element on this sphere here has a lower bound of greater than 0. In other words, these norms do not get arbitrarily close to 0. There is a gap between them and 0. And equipped with that, we can then get the domination in the other direction that we are seeking. Alright, so let's do the proof. And the proof of this one is beautiful. So suppose that what we have is not true. So in other words, instead of there exists a k where everything works, every k has something that doesn't work. Well, that means I can find a sequence of things living in S, not B. Oh, Jesus Christ. Absolute train wreck, as always. I can find a sequence of elements whose norm length is all less than 1 over n. They can get arbitrarily close to 0. But Not by 1. What is this? But then we know that there is... Then there exists. That was from a different version, where I had the previous two propositions together in one thing. I split them into two, and I forgot to fix that. But anyway, so because now we have a sequence living in the sphere, we can find a convergent subsequence. However, we know that the norm is dominated by the infinity norm, so we know that the subsequence will converge with respect to the norm, but then, taking the limits of our norms, tells me that our norm of x is equal to the limit of these norms, because we are convergent and you can pull limits in and out. And note that these were chosen so that the lengths were less than 1 over n, so the subsequence is less than 1 over mk, but as you let k go to infinity, that just goes to 0. So the norm of this must equal 0, which means I have the 0 vector, but that's contradictory because x was chosen to be in the sphere of the infinity norm, right, and that gives you that, yeah, it's equal to 1. And 0 is equal to 1, which is no good. So it's got to be that there is some k that bounds these below. Neat little proof. It's always a good proof when you prove 1 is equal to 0. Alright, so we know that the infinity norm is dominated by, the norm is dominated by the infinity norm, so now we want to prove that the infinity norm is dominated by any norm. So, point 1 gives me a k, so that my norm is greater than everything hanging out in S, not B. So now take an element out of Rn, set C equal to 1 over k. Two possibilities. If it's the 0 vector, well, then the infinity norm is 0, and so is the norm, so we got 0. We have equality. If it's non-zero, then I could divide out by its infinity norm length, which lands me in the set S. And so we know that that's greater than k, but we can factor out this scalar, and it's strictly positive, so I can multiply both sides by it, and then arrive at this. Note that you divide the k over. So, regardless, we find that the infinity norm is dominated by the norm. Beautiful. And that takes care of the proof. So now we know that any two norms are equivalent because any norm is equivalent to the infinity norm, so by transitivity, any two norms on Euclidean space are equivalent. We proved it. So there you go. The p-norms, while computationally are different, qualitatively they are not. Convergence will always be the same. Not only will your sequences converge, they will converge to the same thing. Alright, and as always, when the math gods let us prove something, they want us to use it, so let's go ahead and use norm equivalence in Euclidean space to get an upgrade of our one result that sequences in the sphere have to have convergent subsequences, and here we see that it does not matter which norm you use. We proved it for the infinity norm, but it's good for any norm. And we're going to make use of this when we get to our next goal, which is matrix norms. Okay. So the infinity norm is dominated by our norm, so there is some C, so the infinity norm is bounded above by C times the norm. Alright, define a sequence as follows. Take our original sequence that lives in the sphere of our norm and divide out by 1 over C. Now, our hypothesis ensures that the following is true. The infinity norm of the y-n's have to be less than or equal to C times their norm. So the C comes in and cancels, that gives us our norms over x sub n's, but then we get that's equal to 1. So we have a sequence of elements whose infinity norm is less than or equal to 1. So we know that it is convergence. It is convergent. There is a subsequence that converges to some element y. Now, since norms are equivalent, that means that our subsequence, so if we look at that same subsequence, but now with the x terms instead of the y terms, that's going to have to converge to y times c, because the relationship between the x sub n's and the y sub n's is multiplying by c. So that means that this subsequence has to converge with respect to the infinity norm, which means it converges with respect to our original norm, and since all of these terms have length 1, it's got to be that the limit has length 1 as well. So, hey, pretty sweet. So, with norm equivalence, we now see this convergent subsequence property is universal to whatever sphere you choose. And as we're going to see, it's going to help us a lot when we want to define the norm of a matrix. All right, and with that, we are finally in position to talk matrix norms. Finally. All right. So, given a norm on Rm and a norm on Rn, then in m by n matrix, this set can be formed. So you look at the length of A times x. Now A times x lives in Rm, so we'll use the A norm for that. And the things you multiply by live in Rn, so you look at their B norm, and as we just saw, it's pretty important to look at the sphere, so the set of all things of norm 1. So we're going to look at that set. Now, as we demonstrated, when A and B are the Euclidean norm, this set has a maximum. It's the largest singular value of our matrix. Ooh. It turns out that the set always has a maximum no matter which norms you use. And that shouldn't be shocking because, well, we proved that for the 2 norm, it has the largest value. And all norms are equivalent, so this should always have a max, but of course you gotta prove that. The proof's pretty neat. So the first thing we want to verify is the following. Multiplying by a matrix does not affect the length that much. Or, in other words, there's sort of a predictable way of getting the length relationship. So we kind of saw this with the singular value situation, but here we see that we can get that sort of same inequality. So before we proved this with the 2 norms and k was the largest singular value, here we see that it doesn't matter what norms you have, you can always find a k that works. Alright, so we begin by letting C be the maximum of the A lengths of A times the standard basis elements, but we also throw in a 1 to make sure that C is strictly positive. Because it is possible that A times all of this is equal to 0, but we want, of course, a strictly positive thing, so we just throw in 1. The 1 norm is dominated by B, so we can find a D, and the reasoning for the 1 norm will become apparent in a moment. We'll set K equal to the product of these two. Now it's a product of 2 non-strictly positive numbers, so our product's strictly positive. Now if we look at the A norm, well, we know that X breaks up like that. We multiply A across. We apply triangle inequality. Each one of these terms is less than C, and oh, look at that, we get the 1 norm, which we know is dominated by B, and then we arrive at the following. Alright, now one use of this is that now we're going to prove that something quite nice happens with limits and matrices. So now one of the other algebraic operations we see interact accordingly with limits. If you take the limit of a matrix times a sequence, it's the same thing as the limit times the matrix. And note here the convergence doesn't care about what norms are going on. And note that these what I want to say is note these limits are actually different norms. This limit here is the A norm, and this limit is the one for the B norm, right? They are on different sets. But again, they're equivalent, so, you know, life's good. Alright, and this one is super easy because we just proved that the A norm of a matrix times a vector is always less than or equal to k times the B norm of the vector. So another way of thinking of that is that the output of my linear mapping A times x does not exceed, is always bounded above by the, proportionally to its inputs. Alright, well, we can find that epsilon, or let epsilon be greater than 0. We can find a point where the input sequence gets less than epsilon over k. So then if we look at ax minus a times the limit, we know that we could factor a out. We then get that less than or equal to k times the b norm, but this can be made less than epsilon over k, and thus we pick up our epsilon and get that we can pass limits in and out of matrix multiplication. Beautiful. Alright, now equipped with this, we prove the star of the show for today, which is that, hey, if I look at the lengths of A times X with respect to the A norm, and my vectors are all length 1 with respect to my B norm, this set will have a maximum. Alright. So first things first, we immediately see that the set has an upper bound, because we can find a k so that the matrix times any input is bounded by k times the input's length. So for all things with length 1, these are always less than or equal to k, so it's bounded above, which means that there's a smallest upper bound we can find. I claim that that is the maximum. Now, of course, you need to verify that it's actually in the set, so that's what we're going to do. We're going to find a x so that a times x is equal to alpha. Now, that's the smallest upper bound, so if I subtract anything off of it, it's no longer an upper bound, so we can find something whose length is bigger than it. All of these have length 1, and it's a sequence, and oh, wouldn't you know it, we prove that all such things have a convergent subsequence. And then taking the limit across the board will get me that the limit of the sequence, the subsequence here, is going to have to converge to alpha, and this converges to something, and limits go across norms with no problem. So we have found our x so that a times x is equal to alpha. That means alpha is in E, so that means it has to be its maximum. So not only is it an upper bound, and it belongs to the set, guaranteeing that it's the max. Alright, so then this lets us define the matrix norm induced by these two norms. And you can in fact prove that this is a norm. Again, the details I have in the type notes just to finish this off for today, and so our video is not like, horribly long. It's already on the longer side. But anyway, I will conclude by noting that an absolute classic pastime of linear algebra is to compute the value of a matrix norm. And the classic one is that the norm induced by the two norms is in fact the largest singular value. Very famous result. There are all sorts of combinations you can do and try to compute. There's all sorts of interminglings of the one norm, the two norm, and the infinity norm that people are very interested in. And you can get various proofs associated with those. But going a little bit beyond the scope of what we wanted, but we now finally have a way of defining the length of a matrix. We have a norm for it. Alright, and with that, that gets us to what I wanted to get to, defining the notion of matrix norm. And with that, let's conclude, and I'll see you next time in person, and we get some more fun stuff to talk about.